Hello and welcome to lecture 33 of our Essentials of Semiconductor Device Physics course. In this lecture we continue our analysis of p-n junctions out of equilibrium. So last time we learned that the current of holes in the n side, in the n-doped region, is only a diffusion current. It has no contribution of drift current. And at the same time, the current of electrons in the p-doped region is also only a diffusion current. So this realization motivated the choice to calculate the total current. We're going to calculate the total current by calculating the contribution of the current of holes evaluated at this point. So we're going to evaluate this current at this point and the current of electrons at this point. So we're going to evaluate this current at this point. And since the current across the depletion region is almost constant, we can add up these two contributions to get the total current. So we're going to get the total current by adding the current of electrons, which is only a diffusion current at this point, and the current of holes, which is also only diffusion current at this point. That is then our job this time, to find the total current by finding this current and adding them up. So we want to find J in terms of N and P, in terms of the concentration of charge carriers. And then the next time, the next lecture, we're going to start from this expression, we're going to derive this in this lecture, to then find the relationship between J and the external voltage, which is the Shockley equation. So since this contribution here is given by this current evaluated at this point, mathematically this is the expression that we need to evaluate to get this contribution. And also for the current of holes, this is the expression we need to evaluate to get this contribution. Now, to evaluate these derivatives, we need to know how N and P depends on space. But we have already encountered this problem before in lecture 17. In lecture 17, we found that when transport is by diffusion, which is the situation here, and when we have a loss mechanism, which is also the situation here because we have recombination of holes in the N side and electrons in the P side, so we have a loss mechanism. So in this situation, transport by diffusion with a loss mechanism, the concentration decays exponentially. And we derive this expression for the concentration of holes. We have a similar one for the concentration of electrons in lecture 17, and recall that LP here is the diffusion length of holes, which is given by the square root of the product of the diffusion coefficient and the lifetime of the recombination process. Now you need to be careful about how to interpret this result because there is a subtlety. And this has to do with the fact that this loss mechanism must be a net loss mechanism. But besides having a loss mechanism, we also have generation. We have a gain mechanism. So recall from lecture 30 that we briefly discussed that in equilibrium, when the semiconductor is in equilibrium, we still have a recombination rate. But this recombination rate is compensated by the opposite process, which is the thermal excitation of electrons from the valence to the conduction band. So this thermal excitation is a generation process because it is generating free electron hole pairs, because every time an electron is excited from the valence to the conduction band, it creates a new free electron hole pair. So when we are in equilibrium, the two processes compensate each other. They are equal. So the net loss mechanism is zero in equilibrium. Now, let's take, for example, this n-doped region. When we are in equilibrium, we have recombination and we have generation. Now these two mechanisms compensate each other and the net loss is zero. Now suppose that we are at forward bias condition. We are out of equilibrium. Now there will be new holes arriving at the n-doped region. So it is these new holes, this excess of holes in the sense of excess over equilibrium, which will suffer a net loss mechanism. So that means that the loss mechanism applies only to the excess with respect to equilibrium charge carriers. So this P, for example, cannot be the total concentration. This must be the concentration of excess charges, of excess holes. After all, we have already discussed that away from the depletion region, these excess holes will all have suffered recombination, but the concentration of holes itself does not go to zero. It goes to the value of equilibrium. So the net loss mechanism applies only to the excess with respect to equilibrium charge carriers concentration. So it is convenient to express the concentration of holes explicitly in terms of the concentration in equilibrium plus the concentration of excess holes. So this is the total concentration. This is the concentration of holes in the n-doped semiconductor when the semiconductor is in equilibrium or when it is out of equilibrium. This term here is the concentration of holes in the n-doped semiconductor when the system is in equilibrium. And this term is the concentration of holes in the n-doped semiconductor when we take the system out of equilibrium. So this term refers to these holes that diffused from the P to the n-doped region. And of course, we're going to have a similar expression for the concentration of electrons in the p-doped region. So since the net loss mechanism pertains only to the excess concentration, this equation that we derived in lecture 17 actually pertains to the excess concentration, to Pe of x. So we have now an expression for the concentration of excess holes in the n-doped region. It decays exponentially, governed by the diffusion length, as we learned in lecture 17. And I've set the origin here to lie at this point. So this is why we have this term here, because we want the origin of the exponential decay to be here. So when we replace x with xn, in other words, when we evaluate this concentration at this point, we must get this point, and that's exactly what we get because we're going to have xn here, this is going to be 0, and this is going to be 1. So this is just the boundary condition that imposes that the concentration at this point is given by this value. And we also have the boundary condition that the excess concentration goes to 0 as x goes to infinity. When x goes to infinity, the exponential goes to 0, so this term goes to 0. But the total concentration does not go to 0. It goes to the concentration in equilibrium as expected. Only this term goes to 0 as x goes to infinity. And here we have a similar expression for the concentration of electrons in the p side. The origin now is at the point minus xp, so the boundary condition now is that the concentration at this point must be this term here. So when we replace x with minus xp, we get the exponential will be 1, so we're going to get that this term will be equal to this as expected. And also notice that the other boundary condition is that this concentration must go to 0 when x goes towards minus infinity, negative infinity. That's why we need the positive x here, because now we are requiring that when x goes to minus infinity, then this concentration goes to 0. And of course, this term here goes to 0, when x goes to minus infinity, in other words, very far away from the depletion region. But this term, the total concentration, does not go to zero. It goes to the value in equilibrium. Okay, so now we need to evaluate this derivative and this derivative to find this current and this current. Let's begin by evaluating this derivative here. Recall that we are interested in the derivative in the p-doped region, and after we evaluate it, we're gonna take the value at the point minus xp. So this is the derivative of n. We're expressing it in terms of the concentration in equilibrium plus the excess concentration. But the concentration in equilibrium must be constant across the p-doped region. After all, this is the concentration in equilibrium. This is just the concentration of free electrons in a p-doped semiconductor. So this cannot depend on x. So that means that this term is constant within the p-doped region. So that this derivative here must be 0. So we have only the contribution of the excess concentration of free electrons. So since this derivative reduces to this, all we need to do is to take the derivative of this expression. It's very simple. We have the exponential. The only thing that happens when we take the derivative is that this term will drop. So we have this term because we are taking the derivative of this exponential, and the rest is the same. And now we evaluate this derivative at the point minus xp, because that's exactly what we want to get the current at the point minus xp. So evaluating this derivative at the point minus xp, we only need to replace this x with minus xp, like we've done here. So we're going to get a 0 here, the exponential will be 1, and we're going to end up with this expression for this derivative evaluated at the point minus xp. So using this expression over here, we get this expression for the current of electrons evaluated at the point minus xp, so for this current over here. Now we evaluate the derivative of the concentration of holes in the n side. We again have two contributions, but this derivative here is 0, because in the n side this is not a function of x, it's constant. So we have only this term contributing to the derivative, so this derivative reduced to this, so all we need to do is to evaluate this derivative. So we have exponential of minus x over Lp, so the derivative will drop this term. So then we evaluate it at the point xn, so we replace x with xn, we have xn here, this is going to be 0. So this derivative here reduces to this term, and when we use this term over here, we get this expression for the current of holes evaluated at this point. So this term here is this term here. So that's it. Now we just adapt these two contributions and we get an expression for the total current in terms of the excess concentration of free electrons and the excess concentration of holes. Notice that if the system is out of equilibrium, then these terms are different than 0. But if the system is in equilibrium, in other words, we did not connect the p-n junction to a circuit, then these terms are 0 and the current is also 0 as expected. So this form of the current is still not useful for us because we want to have an expression of the connecting the current with the external voltage, because that's what we need to analyze circuits involving p-n junctions. So in the next lecture, we're going to find a way to express this term and this term in terms of the external voltage. And that will lead to the famous Shockley equation. So I see you next time.